And can everyone see my PowerPoint slides? Very good. Thanks for the thumbs up. Appreciate that, Corinne. So tonight we're going to talk a little bit about descriptive statistics. And I know that we have a test coming up right away, but believe me, this is a pretty dang easy test. This is to get you familiar with using web-based calculators, and that way you're going to be very familiar with what we're doing on Thursday. And if you go through the practice questions and things like that and practice a little bit between now and then, and if you want to work with your teammates, I think you're going to be very prepared. You're going to knock it out of the park on Thursday. So anyway, all right. So this is descriptive statistics. Um, Talk a little bit about scales of measurement first, because that will come up as a theme throughout this class. There are different ways of measuring um, variables, and measurement simply means giving something a number. That's really what a measure is. If I were to rate you on how good a student you are, and I gave you a 7, you'd probably be thinking like, is that good or bad? If that's out of 100, that's pretty lousy. If that's out of 10, that's not bad. But that's an example of measurement. And for scales of measurement, um, they get more precise as you go from top to bottom here. So we start with nominal or categorical. Nominal categorical measurement is simply using numbers to distinguish or separate um, instances of variables from each other. So a very easy example of that would be, let's say that I wanted to make some very um, traditional assumptions about gender. And let's say I wanted to give every male in the class a 1 and every female in the class a 2. That would be an example of categorical or nominal measurement. Um, Jersey numbers on a basketball team, soccer team, football team, anything like that, that's an example of nominal or categorical measurement. And sometimes that has some meaning. Most of the time it doesn't. It's just like, yeah, who was the penalty on? It was on number 44. That's the reason. Um, the next level is ordinal, and ordinal is also used to separate and distinguish, but the numbers as they increase also represent something, a quantity that's either increasing or decreasing. For example, go back to me rating students in terms of how good a student you are. If I give somebody a 7, you're probably thinking like, well, as the numbers go up, does that mean it's the better student? Well, yeah, that makes sense. So if I give somebody a 10, that means that I think they're a better student than the one that got a 7, who I also think would be a better student than the student I gave a 3 to. Now, the thing about ordinal is there's an order there. 3 is worse than 7, and 7 is worse than 10, but we don't know if the exact distance between those numbers is precise. In other words, is 7 much better than a 3 than 10 is from a 7 because there's 4 versus 3? We don't know that with ordinal. All we know is there's an order. So, for example, if we pick the Kentucky Derby first 3 places, we're not saying anything about the distance that separates those in terms of how many lengths or something like that. We just say that horse came in first, that one came in second, and that one came in third. Interval is a little bit more precise, and that means that those distances between the numbers are precise. And the difference between a 6 and an 8 is the same as the difference between an 8 and a 10. That's the same length, that's the same distance. That's meaningful. Now, there's very few examples of interval variables on the planet. One is like the Fahrenheit scale. But most of the time, we'll talk about interval/ratio variables where there's precise distances between the numbers, and also they have a meaningful 0. And that's what ratio means. The 0 represents nothing. So I gave the example of a Fahrenheit scale for temperature. Centigrade or Celsius also is interval, it's not ratio. Does anybody know what the only ratio scale of measurement is? Really big chance for one of you right here who's had a science background. Kelvin. If you measure something in Kelvin, 0 in Kelvin means absolute zero, which means no molecular activity whatsoever. That's as cold as you can get. Okay, so yeah, we'll talk about mainly three types of scales of measurement. Now, if you're wondering how those apply, for example, if I've got nominal categorical data and I want to know something like what's the variability, the range is really the only measure that's appropriate. If I've got something that's ordinal, then the interquartile range or semi-interquartile range is the only appropriate statistic for that. And if I want to know what's the spread on interval ratio, it might be something like the variance or standard deviation that's appropriate there. And I can't use standard deviation and variance with ordinal or nominal categorical because they don't have precise distances between those numbers and it doesn't make as much sense. Okay, moving right along. And if you have a question, I'm not seeing much right now, so you might have to just unmute and interrupt me. So let's talk a little bit about statistics. So statistics, plural, is a field, right? We can study statistics, and we'll be studying a lot about statistics in this class. Statistics can also be plural. I can talk about t-tests and ANOVA and chi-square and Kruskal-Wallis. Those are all statistics, plural. But a statistic, singular, simply means that that is a number that is representing a sample. That is a number that's representing a sample. So a statistic would be like the mean or average. It would be like a standard deviation. It would be um, the sum of squares. But that's pertaining to a particular sample. When we use the same concept and refer to a population, and you know the difference between samples and populations. Samples are drawn from a population. If I were to go out there and randomly select 30 third graders, then I'm looking at a sample from all third graders possible. And all third graders are in a population. Okay. So statistics come from samples and parameters come from populations. So if I talk about the average height of all third graders in the United States, that's a parameter. Now, rarely do we get access to everything in a population because we don't have the money, we don't have the time. Imagine trying to measure the weight of every adult male in the United States. It would be impossible to be able to do that. It would cost way too much money and time. So to estimate what the average weight of all adult males in the United States is, we would try to get a representative sample. Representative meaning I've got the same percentage of African Americans, I've got the same percentage of Asian Asian Americans, and so on. So that statistic, parameter, sample, population, we'll be coming back to that a lot throughout this course, but those are important concepts to know. Okay, so let's jump into getting our hands dirty with some data. So what I've got here are data for 6 students, and these are number of miles ridden on a stationary bike in 30 minutes. Okay. And you could view this as a population if you wanted to. That might be the 6 students that are in my freshman geology class. And if I only wanted to draw inferences about that class, then I could treat that as a population. But rarely do we treat such small sample sizes, such small groups of numbers as populations. More typically, what I want to do here is if I've got 9th grade students and I want number of miles ridden on a stationary bike in 30 minutes, I want to take what I've got from the sample and see what I get and then use that to estimate what I think the average number might be in the population or the typical number of miles ridden in 30 minutes in the population. So that's what I've got here. I've got 6 different scores, and we're going to go through and just do a few calculations to come up with some different statistics. Let's see if I can get my slides working here. All right, so most of you are familiar with the mean, also known as the arithmetic mean. There are different types of means. In case you're wondering, why would they call it the arithmetic mean? Isn't a mean a mean? No, there's a thing called the harmonic mean. That's for music majors mainly. Just kidding. It's my first joke of the evening. That has nothing to do with music. But the arithmetic mean is what you're most familiar with. That's also known as the average, right? So when someone says average height or average income or something like that, or what's the average score on the test we just took, that's what we're talking about, the arithmetic mean. And the mean is defined as the sum of the raw scores, which sum, S-U-M, means add them all up. Take all the scores and add them up. That's what a sum means. And they're called raw scores because that's how we originally obtained the data. We haven't done anything to change them. Raw scores are in their original form, just like a raw vegetable. We haven't done anything to it. A raw score is in its original form. And we divide it by n. Little n is the number of scores in a sample. So in this particular case, n is 6 because I have 6 scores. And if I add up all of those scores, I get 30. If I divide that by n, 30 divided by 6 equals 5. And so 5 is the average or mean number of miles ridden of those 6 students. Everybody with me so far? When you're studying stuff like this, the last thing you want to do is fall behind and hit a point where you're like, I have no idea how the heck you came up with that. If you reach that point ever in this class, to ensure that you're getting your money's worth out of this class, you should flag me down and say, hold on just a minute. And again, the way I'm viewing things right now, I'm not viewing the whole class. I'm only viewing a few of you. So you may have to go in and just say something to interrupt me. Okay, so we've got number of miles ridden on a stationary bike in 30 minutes. We've got the mean is 5. Did I really have 2 different screens like that? That's kind of weird. Oh, okay. I guess it was just twice. All right, so now what we've got is different types of scores. What this thing's doing. Having some weird stuff going on with my computer. So you can see I've got X, capital X at the top here. X is a symbol and it stands for a raw score. Capital X always stands for a raw score. So I've simply got a column there of the raw scores, which you've already seen. And then you can also see I've got a set of mean scores, right? Those are not very nice scores. They're means, just kidding again, just seeing if you're awake. The mean score is the average for all those set of scores. And if I put down 6 mean scores, you can see, not surprisingly, that the sum of the mean scores is equal to the sum of the raw scores. If those weren't equal, then that wouldn't make much sense. So why do I put all those down? Well, because the next thing I'm going to look at is lowercase d, and that stands for difference scores, difference scores. And I calculate my difference score by taking the raw score and subtracting the mean from it. So X minus X bar is a difference score. So you can see for Bill happened to ride that bike 5 miles, and Bill's raw score of 5 is the same as the mean score. So the difference score for Bill is 0. That 0 tells us something. It tells us 2 things, really. It tells us how far the raw score is from the mean. And for this one, it's right there. It's not far at all. And for Susan, who rode 4 miles, it tells me that her raw score is 1 away from the mean, but it's also negative, which means that Susan's raw score was 1 below the average or mean. So those different scores could be negative and positive. And the thing about the different scores is when you sum them up, they should all add to 0, which makes sense if you think about it. So I've got sum of X equals 30. The sum of the mean should also equal 30. and the sum of the different scores should equal 0. Now, I've also got a d squared there, and that is the squared difference scores. Squared difference scores. And you can see all I'm doing there is squaring those difference scores. So -1 squared is 1. I'm removing the negative signs. Right? And when I sum all those up, I get 24. Does anybody know what 24 represents? You just yell this out if you know what it is. It represents the sum of the squared difference scores, which we can even say it a little bit shorter. We can say that's the sum of squares. And sum of squares, or SS, capital SS, is used quite frequently in statistics. And that means the sum of the squared difference scores. Squared deviation scores. I've been using differences. You can also use deviation, which is more common in statistics, deviation score. And then if I want to calculate the variance is the sum of squares divided by n minus 1. And so n minus 1 here is 6 minus 1, which is 5. If I take that 24 and I divide it by 5, I get 4.8, which is my variance. Now, that is the formula for a variance for a sample. And the sample is always divided by n minus 1. If I wanted the variance formula for a population, I would just divide it by n. N minus 1 is what's called a correction term. And the reason why is that if you're using a sample to estimate what the population might be, variance calculated by just dividing by n tends to underestimate the population variance. So when we add that correction term, n minus 1, that makes the denominator a little bit smaller, which inflates or increases the overall variance for a sample, which makes it a better estimate of the population variance. And then the standard deviation, I'm sure some of you have heard of standard deviation before. That's simply the square root of the variance. So if you take the square root of 4.8, that's about 2.19, and that's the standard deviation. All right, moving on to the next. Here's then, here's an example. See, I've got 6 scores here. Let's suppose I have one more student come by, and that student's name is Clark Kent. And before I mention Clark Kent, Jill, I believe you have your hand up.
Y'all just bear with me. So when we find the answer to the standard deviation, the answer, that's all we call it, is the standard deviation, or how would you go back to the actual problem itself? So the standard deviation is the mile?
No.
Okay.
Yeah, that's a really good question. The standard deviation is actually, and I'm not joking when I say this, it's kind of a magical statistic, and I'll show you why when we get to correlation, calculating correlations. But it's sort of the standard deviation. The typical student in this data set, that's the typical distance they are from the mean in terms of their score. That's what that standard deviation means. That the standard deviation score is about 2.19. So that means that on average, a student is scoring about 7 or 3 or something like that on average. That's what that means. Yeah. Okay. So I add one more student because I want 7 scores instead of 6, and I bring in this student named Clark Kent, and he gets on the exercise bike and he rides in 30 minutes for 493 miles. All right. You all know who Clark Kent is, right? We're not that old. Okay. So the reason why I want to show you what this does is that when you have one score in your data set that's very much higher or very much lower than the rest of your scores, those scores are also called extreme or outlier scores. That can really mess things up when you're doing traditional statistics. So you remember going back, our standard deviation was about 4.8 and our variance was about 4.8. Our standard deviation was about 2.19. Well, look what adding a score of 493 does to both of those. And for one thing, it takes the mean and makes it 74.71. And if you're looking for the mean as a measure of central tendency to sort of describe what's the typical score in my data set, well, having an extreme score really screws things up because 74 miles in 30 minutes doesn't do a very good job of describing your typical student, right? So for one thing, it messes up the mean. For another, it inflates your variance. The variance now is over 34,000 and the standard deviation is up to 184, which means that, your typical student is around 184 different than the overall mean. So that's what's called adding an outlier here. And when you have an outlier in a set of scores like this, where it really, throws everything off, then you don't want to use your typical, what are called parametric statistics, like mean, standard deviation, variance, sum of squares. You want to use what's called more non-parametric statistics, which is what we're going to cover next. So parametric versus non-parametric statistics. The mean and standard deviation are called parametric statistics. To use those, you have to assume that your data are interval ratio, which for numbers of miles ridden on an exercise bike, that is interval ratio. You can have 0, you can have 14 miles, and the difference between 14 and 13 is the difference same as between 2 and 3, right? That's good interval ratio data, but it has to have a normal distribution. And we can talk about shapes of distributions, but the bell curve. You ever seen a bell curve? If you have an extreme score that's added to the set of scores, what that does in this case with Clark Kent's 493 is it takes that right side tail of the distribution and it pulls it way out there. And it makes that distribution skewed, which means that you shouldn't be using parametric statistics to describe that data set. So if you have something like that, or if you simply have ordinal data, if those scores represented, like rating those students in terms of how good they were in your class as a student, then you would want to use what are called non-parametric statistics. And the median and the semi-interquartile range are called non-parametric statistics, and they're more appropriate with ordinal or non-normally distributed data. And I'll show how that works. That SIQR, by the way, stands for semi-interquartile range. And everybody knows what a median is. A median is simply, if you order the scores from largest to smallest or smallest to largest, it's the score that would fall right in the middle and cut that set of scores in half. Kind of like a median on a highway or interstate divides two lanes of traffic that are going in opposite directions. Okay. So we'll go back to our original set of 7 here, scores. And you can see that if I have 7 scores, if I have an odd number of scores, the median is going to be an actual score in the distribution because I'm going to order them from smallest to largest. And the median here, the middle score, is 5. So in this particular case, the median, or also known as quartile 2, because quartiles, by the way, are dividing the distribution up into fourths. And second quartile means 2/4 or 1/2. That means 1/2 of the scores fall below that number and 1/2 fall above that number. If you want to figure out quartile 1 and quartile 3, quartile 1 is the point where 25% of the scores fall below. Then you can simply take the median and figure out sort of the median for the scores below the median. And you can see that I have the median of 5 here, and I've got 3 scores below it. Well, that's an odd number, so the first quartile is going to be 4 because that's sort of divides the lower 3 scores, and quartile 3 is going to be the score that divides the higher of the 3 scores. The interquartile range is simply subtract quartile 3 from quartile 1. And that's 8 minus 4, which is 4. The semi-interquartile range, which is a statistic that's more common than the interquartile range, is simply the interquartile range divided by 2, which in this case would be 4 divided by 2, which is 2. Now, first off, think back to what our original set of 6 scores looked at with the mean and standard deviation. Remember that had a mean of 5 and a standard deviation of just about 2, a little over 2. Well, if I use the median and the semi-interquartile range here, even though I've got a very extreme score, you can see that the median and the semi-interquartile range are not affected as much by an extreme score. The median's 5 and the semi-interquartile range is 2. So the reason why we use these non-parametric statistics is that they are less sensitive to extreme scores. You've also heard of the range as a statistic, right? That's where the deer and the antelope play. Just kidding again. That's another joke. The range in statistics is what's the distance from the lowest score to the highest score. Now, the range is very much affected by adding Clark Kent's 493 here, right? The range gets very much higher. But again, the range is really only appropriate when we're talking about nominal data. If we had like, genders, and we gave a 1 for this gender and a 9 for this gender in terms of how many categories, then what's really important for us is how many different categories of gender do we have? And by the way, some people use more than 2 categories of gender, right? There might be 4, there might be 7, there might be more than that, right? So what's important with the range is we want to know what's the range of categories. Okay, and then the mode is simply the most common. And when you have categorical data, the mode is really the only measure of central tendency that's appropriate. For example, let's go back to the example of using a real simplified version of gender and saying, I'm going to assign males 1 and females 2. Well, you don't want to do an average and say, you know what, the average gender in my class is 2.1 or 1.7 or something. That doesn't make much sense. What you'd rather have is like, yeah, there's 47 females in my class. That's the most common. So the most typical student in here in terms of gender is female. That's what the mode does for you with nominal and categorical data. We have a hand up. Melody. You unmute.
There we go. Just took me a second. So
Yeah.
I wanted to go back to what you were saying about range and those extreme scores. And when I'm thinking about this, I'm thinking about Dibble's data. And like, I guess my question is like, when you do have really large data sets, I hear what you're saying about nominal data, like that there's times that you just want to know like what the different categories are. But
Yep.
what happens whenever you have these really large data sets? Like with Dibbles, where you're taking all of the reading data for all of these kids, does the range play into that at all whenever you're
The range is only important if that's an interesting research question to you, right?
okay.
So let me give something a little more understandable here. Let's take like the SAT, for example. The range on the SAT, the highest score is 800 for the verbal section, right? And usually the lowest, I think, is 200. I don't think you can even get lower than 200 if you don't answer anything correctly. So you might want to understand the range there in terms of if someone says, hey, I got a 650 on the SAT verbal and no one knows anything about the SAT, if they want to know whether that's good or bad, then you could explain the range to them. Or you could say, this is the highest score, this is the average score, this is the lowest score, something like that. It all comes down to, if you want to use the range, does that answer an interesting question for you? That's pretty much it.
Okay.
Yeah, yeah. But we'll talk more about Dibbles later in terms of
Okay.
reading tests. Yeah. All right. Okay. So yeah. So if I go back and I remove Clark Kent from this, you can see it doesn't do a lot to the non-parametric statistics. If I remove that 493 and go back with a sample of 6, then my median now falls between two numbers because I've got 3 higher numbers, 3 lower numbers, and to divide them in half, my median falls between 4 and 5, and my median is simply the average of the two scores in which it falls between. So 4.5 is my median. My interquartile range now will become 3 because my upper quartile, my third quartile is 7, my quartile 1 is 4, and it goes from 3, and then my SIQR is half of that. So by removing Clark Kent, my SIQR went from 2 to a 1.5. So you can see that these non-parametric stats are less sensitive to bias in extreme scores. That's why we use them. The range obviously was greatly affected. The mode, on the other hand, wasn't affected at all. Okay, so now what I want to do is I want to show you how to do some of this stuff.
I have a quick question.
Yeah.
Yes. You listed Susan as the Q1. I guess it doesn't matter whether you pick Susan or Juan, or do you pick the Q1 based on like a subordinate
that's
ordering?
A really good question. Do I use Susan's score of 4 or Juan's score of 4 for the Q1? It doesn't matter. They both have a score of 4, and it's not that Q1 is Susan. It's that Q1 is 4. That's what's important. Yeah, yeah.
Thank you.
Susan is not being shown preferential treatment over Juan there. That's what's important. Yeah. Okay. I'm going to share my screen again now and show you how to do this using Vassar stats. So let me go to share again, and I'll go to my website and make sure I can see everybody. Everybody's seeing Vassar stats? This will be a common website for you to use. In fact, I would bookmark that if I were you, because you'll be using this multiple times in this class. So we can do all these calculations much easier than doing them by hand by using online stat calculators. And by the way, Vassar Stats is not the only online stats calculator. There are literally hundreds of them out there. And with the new AI programs now, you might find something that's much better than what I come up with. But I'm just going to show you a few things that I think will be more than sufficient to help you do the quizzes and tests and stuff in this class. All right, so I'm in Vassar Stats right now. And what I'm going to do on the far left side here is I'm going to click on Miscellanea. Miscellanea. And I'm going to go up and click on Basic Sample Stats. If you'd like to follow along and do the same thing and pull up Vassar Stats, that might be a really good thing to do. Because that way you can see what I'm doing, or and that might be enough too. So if you don't want to do it, that's fine. Okay, there will be a recording of this if you need to go back and watch the class. I'll click on Basic Sample Stats, and I'm going to enter in those same original 6 scores that I had at the beginning: 2, 4, 4, 5, 7, and 8. That was my original 6 scores. Now, it's important here, if I hit return another time there, Vassar Stats thinks I've got 7 scores instead of 6. So make sure you don't have an extra return at the end. Make sure that cursor is flashing right next to the last score. And if I hit calculate, that's going to give me a number of those statistics, those parametric statistics that we did earlier. You can see I've got sum of X here. That's the sum of the raw scores. N is 6. That's the number of scores. The mean is 5, which we came up with. Right? Now, something we're never going to use in here, and I don't want you to be confused by this. This means this Greek letter uppercase sigma means sum. X is a raw score, and that superscript 2 means squared. That is the sum of the raw scores squared. We're never going to use that, but Vassar Stats gives that a lot. But don't think that is the sum of squares. You know what the sum of squares is? SS. Always SS for sum of squares. And that's 24, which we had earlier. And then this will give you the inferential or descriptive variance and standard deviation. Inferential stands for the statistic for a sample, and descriptive will be the one for a population. These numbers are calculated using the n-1 in the denominator, whereas these are calculated using just the n in the denominator. Notice how the ones on the left are slightly larger. That's because when you take n-1 in the denominator, that makes the denominator, a little bit smaller, which increases the overall value. So the variance is 4.8, standard deviation 2.1909. Somebody talking? Sorry, I didn't know. Jasmine, yes. I'm sorry, what? You're muted again.
I think it was an accident.
Oh, okay. I'm sorry. I did not want to blow off a question, so she must have just unmuted herself, and that was it. And the standard error we'll get to later. The standard error is something we're going to talk about next week, but you won't need to know that for this week. Okay. So, all right. Now we want to also know how to do median, interquartile range, semi-interquartile range, stuff like that. So I can get out of Vassar Stats, and let's just say I want to Google something like SIQR calculator, semi-interquartile range calculator. Comes up right away, and I've got easy calculation. Look at all these options I've got. The one I kind of like is calculator soup. But again, you can use any of these, but you want to practice with them. And you know how you'll be able to practice with these and make sure that you're coming up with the right answers? Is I've got those practice problems in the module, and there's practice problems for test 1. You can go through, there's practice problems, and then there's the key, and you can work all these out and see if you come up with the right answer. Then you can check with the key to see if you're coming up with the right answer. I'm gonna use the calculator soup one for quartile calculator. This one's kind of cool. And you can enter your data set separated by commas or spaces, which is kind of nice. Vassar Stats wants you to put them all in with like hard returns and stuff. So here I can just do spaces: 2, 4, 4, 5, 7, and 8. Or I could use commas and not have a space. And if I click calculate now, and this is calculator soup, by the way, IQR calculator. It's going to give me the first quartile, the second quartile, the third quartile, the interquartile range. The median was 4.5. Minimum, maximum, meaning the lowest score, highest score, and it gives me the range. That's all I need, right? And if I want to add in that, was it 493? You can see that I'll get the same numbers that I had before. I've got interquartile range of 4, median of 5. And this doesn't give you the semi-interquartile range. Does anybody know how we might get the semi-interquartile range given the interquartile range?
Divide by 2.
Divide by 2. Very good. And then it shows you the range here. So with these two things, calculator soup, the quartile calculator and calculator soup, and the Vassar Stats website for miscellanea and basic descriptive stats, that will allow you to do everything you need to do for test 1. That will allow you to answer all the practice problems correctly. And if you work through all those practice problems before Thursday, and if you want to find a teammate or two and get together like tomorrow night and set up a Teams meeting and say, let's work through some of these together, that's fantastic. Or you could do it like 5 p.m. on Thursday, since class is at 6:30. And that's basically all I've got for the first test. all that stuff I covered is what you need to know for the first test. Notice there's no hard math calculations. Brittany's applauding, so you can't beat that. You have a class like this, you get applause. You can't beat that. All right, if there are no questions, what we're going to do with the remaining time that we have is do introductions so that we can meet everybody, and especially you find out